Hold a magnet above a steel paperclip and release it. The magnet pulls the clip upward, through empty air against gravity. No contact, no wire, no mechanism you can see. The force crosses a gap of open space and moves matter. You have watched this happen 1,000 times and treated it as ordinary. It is not ordinary. The force that lifts the paperclip is the same force that holds every molecule in your body together. The same force that makes light visible to your eye. The same force that carries every radio signal that has ever been transmitted. Electromagnetism is the dominant force at every scale between atomic nuclei and planets. It is the force of chemistry, of biology, of all technology that has ever existed. And the question of why it works, the mechanism by which a magnetized piece of iron exerts force on another piece of iron through empty space, is one of the deepest unsolved problems in the conceptual foundations of physics. The mathematics is exact. The reason no one can answer it is that the answer the mathematics gives is one that human intuition refuses to accept. Feynman was asked this question in 1983 by a BBC journalist named Christopher Sykes. The interview was part of a documentary series. Sykes asked simply, "Why do magnets repel each other?" Feynman paused. Then he said something that most people who watch the clip remember for years. He said he could not answer that question. Not because he did not know the physics. He had spent decades on the physics. He said he could not answer it because every answer he could give would require the questioner to already understand something else equally puzzling, and that answer would require understanding something else. And at some point, you hit the bedrock of the universe, and there is no deeper explanation. The question sounds simple. The honest answer reveals a hole in the floor of our understanding that goes all the way down. To see why, start with what we do know, and what we know is precise enough to be startling. Every electron in the universe carries a property called spin. Not spin in the mechanical sense. The electron is not a ball rotating on an axis. Spin is a purely quantum mechanical quantity with no classical analog. It is an intrinsic angular momentum, a fixed quantity, that every electron carries in the same magnitude, 1/2 times h bar, where h bar is Planck's constant divided by 2 pi, equal to approximately 1.055 times 10 to the minus 34 joule-seconds. This is not an approximation. Every electron in every atom and every magnet on every planet carries exactly this value, not approximately this value. This value, because the electron carries charge and because it carries spin, it also carries a magnetic dipole moment. A spinning charge produces a magnetic field. This is a consequence of Maxwell's equations, published by James Clerk Maxwell in 1865 in his treatise on electricity and magnetism. The electron's magnetic moment, measured in units called Bohr magnetons, is equal to approximately 2.002319304362. That number comes from quantum electrodynamics, the theory Feynman himself helped construct in the late 1940s. It has been measured experimentally to 12 decimal places. The agreement between theory and measurement is the most precise confirmation of any scientific prediction in human history, not the most precise in physics, in all of science. The number is exact to a degree that should stop anyone who encounters it. The magnetic moment of the electron is the engine of ferromagnetism. In most materials, electrons pair up with their spins pointing in opposite directions, one spin up, one spin down. The magnetic moments cancel, no net field. But in iron, cobalt, and nickel, the electronic structure of the atom is unusual in a specific way. The 3D orbital of these elements contains unpaired electrons, electrons whose spins are not cancelled by a partner. Each unpaired electron carries its magnetic moment unreduced. And in these materials, a quantum mechanical interaction called the exchange interaction causes neighboring electrons to align their spins in the same direction rather than opposite directions. The exchange interaction was identified by Werner Heisenberg in 1928, published in Zeitschrift für Physik. It is not a magnetic interaction. This is worth emphasizing. Two magnets attract or repel each other through their magnetic fields. But the alignment of electron spins in iron is not caused by magnetic forces between neighboring electrons. It is caused by the Pauli exclusion principle and the overlap of electron wave functions. Two electrons with the same spin cannot occupy the same quantum state. When their wave functions overlap, their spatial distributions are forced apart, which reduces their electrostatic repulsion. This energy difference, calculated from quantum mechanics, not classical magnetism, is what aligns the spins. The source of ferromagnetism is electrostatics and quantum statistics, not magnetism. This matters. The thing that makes iron magnetic is not, at its root, magnetic. It is a consequence of electrons avoiding each other through the Pauli exclusion principle, which is itself a consequence of the anti-symmetry of the electron wave function under particle exchange. Remove the Pauli exclusion principle and iron stops being ferromagnetic. The magnet on your refrigerator exists because electrons obey a symmetry requirement in quantum mechanics that has no classical equivalent and no intuitive picture. But this is only the first layer of the problem. The exchange interaction explains why neighboring spins align. It does not explain why the alignment survives at room temperature, why it produces the force you observe across an air gap, or why the force follows the inverse square law. It follows each of these requires a separate account. The energy scale of the exchange interaction in iron was calculated by John Slater at MIT in 1930, published in Physical Review. Slater computed the exchange integral, the quantum mechanical overlap of electron wave functions on neighboring iron atoms, and found an exchange energy of approximately 0.1 electron volts per pair of neighboring atoms. 1 electron volt is approximately 1.6 times 10 to the minus 19 joules. The thermal energy available at room temperature is kT, where K is Boltzmann's constant, approximately 8.617 times 10 to the minus 5 electron volts per Kelvin, and T at room temperature is 293 Kelvin, giving a thermal energy of approximately 0.025 electron volts. The exchange energy, 0.1 electron volts, is 4 times larger than the thermal energy trying to randomize the spins. This margin is what allows ferromagnetism to persist at room temperature. Below the Curie temperature, 1043 Kelvin for iron, 1388 Kelvin for cobalt, 627 Kelvin for nickel, the exchange energy wins and the spins remain aligned. Above it, thermal fluctuations overcome the exchange energy, and the material becomes paramagnetic. The temperature at which this transition occurs was measured by Pierre Curie in 1895, published in Annales de chimie et de physique, before the electron was discovered and before quantum mechanics existed. Curie measured the transition point in iron precisely. He did not know why it existed. The explanation required quantum mechanics that would not be written down for 30 more years. In iron at room temperature, the exchange interaction aligns electron spins within small regions called magnetic domains. Each domain contains roughly 10 to the 12th to 10 to the 18th atoms, with a physical size of roughly 1 to 100 micrometers. Within each domain, the spins are aligned, all pointing the same direction, producing a strong local magnetic field. But different domains in an unmagnetized piece of iron point in different directions, and their fields cancel. The iron appears magnetically neutral from outside. Apply an external magnetic field, and the domains whose orientation is closest to the applied field grow at the expense of their neighbors. Domain walls, the boundaries between differently oriented domains, move through the material. They move not by rotating individual atoms but by propagating a boundary at which the spin orientation changes over a few atomic spacings. The Bloch wall, named after Felix Bloch, who calculated its structure in 1932, is a transition region typically 100 to 200 atomic spacings wide, across which the spin rotates gradually from one domain orientation to the next. When the applied field is strong enough, all domains align and the material is magnetically saturated. Remove the field, and the domains partially retain their alignment. This is remanence, the permanent magnetism that makes a refrigerator magnet stick. The domain theory was proposed by Pierre Weiss in 1906 in Comptes rendus de l'Académie des Sciences, before quantum mechanics existed. Weiss inferred the existence of domains from macroscopic measurements of magnetization curves. He measured something he called the Weiss field, an internal molecular field that he estimated to be approximately 600 times stronger than any external field that could be applied experimentally. He could not explain what produced it. The Weiss field remained mysterious for 20 years until Heisenberg identified the exchange interaction as its origin. The number Weiss had measured empirically was the exchange energy expressed as an effective magnetic field. He had measured a quantum mechanical effect using thermometers and magnetometers 20 years before quantum mechanics was written down. The data knew. The explanation came later. Now I want to follow the physics to where it actually leads, because this is the point at which the question becomes genuinely hard. Maxwell's equations describe electromagnetic fields with precision. They predict the propagation of electromagnetic waves at a speed equal to 1 divided by the square root of the product of the permittivity and permeability of free space. A calculation Maxwell performed in 1865, getting a value of approximately 3.117 times 10 to the 8th meters per second, close enough to the then measured speed of light that Maxwell immediately recognized that light was an electromagnetic wave. The equations are exact, Every radio transmitter, every MRI machine, every fiber optic cable operates according to Maxwell's equations. They work, but Maxwell's equations describe the field. They describe how the field behaves, how it propagates, how it exerts force on charged particles. What they do not describe is what the field is. The field is a mathematical object that takes a value at every point in space. It has a direction and a magnitude. It exerts force on charged matter. But the question of what is actually there, what physical thing is present in the space between the magnet and the paperclip when no charged matter is present, is a question Maxwell's equations do not answer. They describe the behavior of something without specifying its nature. This is the problem Faraday encountered before Maxwell. Michael Faraday, who had no university education and could not write mathematical equations, introduced the concept of field lines in the 1840s as a way of visualizing what he called the lines of force surrounding a magnet. Faraday spent years mapping these lines by sprinkling iron filings on paper held over magnets and recording the patterns. He took his field lines more literally than most of his contemporaries were willing to accept. He thought something was physically present in the space traversed by the lines, not just a convenient way of drawing forces, but a real physical structure filling space. In a letter to Maxwell in 1857, Faraday wrote that he wished Maxwell could find a way to express the action of the lines in mathematical form, because his own inability to write the mathematics made it impossible to convince anyone that the field was real. Maxwell responded by doing exactly that. He translated Faraday's physical intuitions into 20 equations, later reduced by Oliver Heaviside to 4, that described the behavior of electric and magnetic fields with complete precision. Maxwell's equations vindicated everything Faraday had intuited. But the question of whether Faraday was right about the field being real, whether the field lines are physical objects or mathematical bookkeeping, is a question Maxwell's mathematics did not answer, and that no subsequent theory has answered definitively. Einstein took a strong view on this. In his 1920 address at the University of Leiden, titled Ether and the Theory of Relativity, Einstein argued that empty space is not truly empty, that the electromagnetic field and the gravitational field together constitute a physical medium that he was willing carefully to call ether, while distinguishing it entirely from the mechanical ether that 19th century physics had rejected. His argument was that the field equations predict effects in regions of space that contain no matter, and a theory that predicts physical effects must be describing something physically real. This was Faraday's position restated in relativistic language. It did not resolve the question, it sharpened it. Quantum electrodynamics, the theory Feynman, Julian Schwinger, and Shinichiro Tomonaga developed independently in the late 1940s, work for which all three shared the Nobel Prize in Physics in 1965, provides the deepest currently available description of the electromagnetic interaction. In QED, the electromagnetic force between two charged particles is mediated by the exchange of virtual photons. Two electrons repel each other because they exchange virtual photons, particles of light, that carry momentum from one electron to the other. The force is a transfer of momentum through particle exchange. There is no action at a distance. There is an exchange. Before following this further, it is worth pausing on what the exchange actually means. Two electrons are separated by 1 nanometer, approximately the diameter of a small molecule. They repel each other. In classical electrodynamics, the repulsion is explained by the field. The force at 1 nanometer separation for two electron charges is approximately 2.3 times 10 to the minus 10 newtons. Tiny by everyday standards. Enormous relative to the electron's own mass, which is 9.11 times 10 to the minus 31 kilograms. The field explanation is precise and predictive. What it leaves unexplained is how a mathematical object pushes a particle that sits inside it. QED answers this by replacing the continuous field with particle exchange. The word virtual is important and widely misunderstood. A virtual photon is not a photon that is very small or very fast or somehow weakened. A virtual photon is an internal line in a Feynman diagram, a mathematical object in a perturbation expansion that represents a contribution to a probability amplitude. It does not have a definite energy or definite momentum. It does not satisfy the relation between energy and momentum that a real photon satisfies. The relation E equals pc, where p is momentum and c is the speed of light. A virtual particle is an intermediate state in a quantum calculation that cannot be directly detected. It is a feature of the calculation, not a feature that can be confirmed by measurement. Feynman diagrams, the visual notation, Feynman invented and introduced in a paper published in Physical Review in 1949, represent the perturbation expansion of the probability amplitude for a given process. Each diagram corresponds to a mathematical term. The simplest diagram for electron-electron repulsion shows two electrons exchanging one photon. The next diagram shows two photons being exchanged. The next shows a photon briefly splitting into an electron-positron pair and recombining. You add the contributions of all diagrams ordered by complexity, and the sum gives the probability amplitude. The precision of QED comes from computing enough terms in this expansion, and from the smallness of the fine structure, constant, alpha, equal to approximately 137.036, which governs how quickly the terms diminish in magnitude. Higher-order terms are suppressed by factors of alpha, so the series converges rapidly enough that computing a few terms gives extraordinary accuracy. In the BBC interview, after explaining that he could not answer the question of why magnets repel each other in a way that would satisfy the questioner, Feynman said, "When you explain a why, you have to be in some framework that you allow something to be true. Otherwise you are perpetually asking why. Why did the universe behave this way? I cannot get deeper than that." He was describing the same structure that every scientific explanation eventually reaches. Every explanation depends on something that is accepted, without explanation. But the interview contains something else that is equally important and less often quoted. Before reaching that conclusion, Feynman spent several minutes explaining why every available analogy for magnetic force was inadequate. He pointed out that people accept the explanation because the atoms inside are arranged to be that way, without noticing that this explains nothing about the force itself. It just pushes the question down one level. He said that if you ask why two magnets repel, and I answer because they're both north poles, you have learned nothing new, because the repulsion of north poles is exactly what you asked about. And if I say because of the electromagnetic field, and you ask what the field is, the only honest answer is that the field is a mathematical object that correctly predicts every experiment ever performed. The field is defined by what it does. Its nature beyond what it does is not something physics currently has access to. Feynman was not dismissing the question. He was being precise about what kind of question it was. There are two types of explanations in physics. One type reduces something unfamiliar to something familiar, the way thermodynamics reduces heat to the motion of molecules, translating an unfamiliar macroscopic phenomenon into familiar mechanical motion. The other type reveals that something familiar is actually deeply strange, the way special relativity reveals that the familiar concept of simultaneous events does not have an observer-independent meaning. The question of why magnets attract belongs to the second type. The phenomenon is familiar. The correct description of it is stranger than the phenomenon itself. And Feynman's point was that any explanation that makes the phenomenon seem less strange is to that extent wrong. The convergence of these threads is not accidental. They point to the same structure. The magnet works because electron spins align because of the exchange interaction. The exchange interaction exists because electrons are fermions, particles with half-integer spin that obey the Pauli exclusion principle. The Pauli exclusion principle is a consequence of the spin statistic theorem, proved by Wolfgang Pauli in 1940, published in Physical Review. The theorem states that particles with half-integer spin must obey Fermi-Dirac statistics. Their wave functions must be antisymmetric under the exchange of two identical particles. This antisymmetry is not postulated. It is derived from the requirements of special relativity combined with quantum mechanics. Remove special relativity, and you can construct a quantum field theory where bosons and fermions are interchangeable. Keep special relativity, and the spin statistics connection becomes necessary. The magnet on your wall is a consequence of the consistency of quantum mechanics with special relativity. The force across the gap, the thing you see when the paperclip lifts through the air, is described by the electromagnetic field, which in QED is described as the exchange of virtual photons, which are mathematical objects in a perturbation expansion. The force is real. The photons are, in a precise technical sense, calculational artifacts. The field is a mathematical structure that encodes everything we can predict about the outcome of any electromagnetic interaction. Whether the field is also a physical substance that exists in the space between the magnet and the paperclip, whether there is something there, in the way water is in a pipe, is a question QED does not answer. It answers every measurable question about electromagnetic interactions to 12 decimal places. It does not answer what the field is. There is one more layer. The spin statistic theorem, the result that connects electron spin to the Pauli exclusion principle, and therefore connects the exchange interaction to ferromagnetism, and therefore connects the aligned domains to the force across the gap, is not simply a postulate of quantum mechanics. It was derived by Pauli in 1940 from two requirements: that the theory be consistent with special relativity, and that the energy of the vacuum be bounded below, that the universe not have states of arbitrarily negative energy that would allow it to collapse. If you require a quantum field theory to respect special relativity and to have a stable ground state, the spin statistic theorem follows necessarily. Half-integer spin particles must be fermions, integer spin particles must be bosons. This is not a choice, it is a consequence. The magnet on your wall is therefore a consequence of the requirement that the universe be stable. If the vacuum were not bounded below, if electrons could have arbitrarily negative energy, the Pauli exclusion principle would not hold, the exchange interaction would not align spins, domains would not form, and ferromagnetism would not exist. The stability of matter and the existence of permanent magnets share the same mathematical root. Pauli proved this theorem, but found it unsatisfying in a specific way. He remarked in correspondence with Heisenberg that the proof was correct, but that it did not give him the physical intuition for why spin and statistics should be connected. He understood the mathematics. He did not feel that he understood the physics. This is a distinction that any honest account of quantum mechanics must preserve. Understanding the mathematics of a result and understanding why that result is true are not always the same thing, and in the foundations of quantum mechanics they are frequently not the same thing. The history of physics is sometimes told as a story of increasing explanation, as if each new theory answers the questions left open by the previous one, and the goal is an eventual complete account in which everything is explained in terms of something more fundamental. The story of magnetism runs in the opposite direction. Newton explained the orbit of planets as the effect of a force, without explaining what force was. Maxwell explained the force as the effect of a field, without explaining what the field was. Faraday thought the field was real, a physical structure in space, but could not prove it. Einstein showed that the gravitational field is the curvature of space-time, geometry, not substance, which answered Faraday's intuition about one force and deepened the question about the other. QED replaced the field with particle exchange, and then replaced the particles with amplitudes, and then replaced the amplitudes with a path integral summed over all possible histories. At each step the description became more precise and more accurate. At each step the question of what is actually there became less answerable. Feynman understood this, and it is why he answered the way he did. He was not being evasive. He was being precise. The honest statement of where physics stands on the question of why magnets attract is, we have an exact description of how they attract, confirmed to 12 decimal places, and we do not have an answer to why the universe is structured in a way that makes that description true. That distinction between description and explanation, between how and why, is not a failure of physics. It may be the deepest thing physics has taught us about the nature of knowledge. The paperclip still hangs in the air. The calculation is exact. The question remains open. Those two facts coexist without contradiction, and the coexistence is not a gap to be filled. It is the result.